got our test on Friday. Hopefully you got my email. I would love to do some review. There's lots of stuff out there posted. We had the quiz returned. Did I put those quiz solutions in here? Did not throw the solutions in there, I don't think. So let me do that quick. Oh, yes, I did. Great. So we had the quiz returned. We can look at that. And this class is really just going to be driven by your questions. And if there aren't a lot of questions, then that's fine. We don't have to spend all class doing it. So it's totally up to you. And so I'm going to just sort of start by looking at the topics and run through a few things. And if you wanted to start looking at some of the review stuff, it's posted on Blackboard, and it's also in our shared Dropbox, right? So there's test 3 practice problems. There's tons of stuff in there. I'm looking at the topics right now, but there's also a review packet, and sort of, as you can see, more specific review. So anyway, let me run through a few of the topics and just say a few things, and then you can let me know if there are specific things you want to see or talk about or whatever.
Note card.
You can use a note card. Yes. Let me make that note here. So can bring note card with notes again. Yeah, any sort of other general questions like that?
Professor, I'm not going to be able to make it in person due to COVID reasons. Would you like me to take it online on Friday?
Yeah, would you send me an email so we can figure that out and set it up?
If you don't want me taking it online, I'll be back on campus on Monday.
Okay. Yeah, send me a message and I'm sure we can work that out.
Good, thank you.
Other questions like that? Okay, so you can see it starts with optimization. So this is there's like, let's see here, yeah. Basically from here on up is differentiation stuff. A little bit. So you're doing derivatives and all these things, right? Optimization, you're finding the max of something. Mean value theorem was a derivative thing. Implicit differentiation is where you have like a function of time, for example, and then you're doing d over dt of that, if you remember that kind of idea. And so that becomes like df dt or f prime. And so it often requires lots of chain rules is the way to remember that. Anyway, so you use implicit differentiation in related rates. And so that's why those two things are oftentimes tied together. They're sort of individual problems for implicit differentiation. We had a whole homework set of those, but then the next homework set was related rates. And the way you set those problems up always involve implicit differentiation. So we can look at that connection there if you're interested. And then the last thing we looked at related to differentiation was L'Hopital's rule. So that's where you have some limit and you end up with either 0 over 0 or infinity over infinity. And so what you do is you can do the derivative of the top function and the bottom function. That's just a quick reminder of what that is in case you forgot. We can look at that too if you want. So those first 5 topics are all about derivatives. So you need to know the derivative rules, obviously, but they're embedded in these larger problems, just to be clear. So, knowing like the chain rule or the power rule, I'm not going to ask you to do those things specifically on this test, but you'll have to do those things, for example, to find the max of one of the optimization problems, right? Or if you wanted to figure out a critical point, I'm not going to say find the critical points on this test, but you need to find critical points in part of related rates, for example, or optimization, etc. The second half, 6 through 10, these are all things related to integration. And maybe one of the sort of saving graces on this test is, I feel like it's, in a lot of cases, a lot of advanced material, but so this is integration. But the difference is, or not the difference, but the nice thing, or one of the nice things, saving grace, if you will, is, the derivative rules are the opposite of the integration rules or vice versa. So if you know the derivative rules, you should kind of already know the integration rules. And so it's not like you have to memorize twice as much in terms of knowing the rules, at least. Just try to keep that in mind. And of course, if there are tricky ones, you can put them on your note card. Hopefully you've already sort of started preparing for this test. And the first thing I always do if I was going to have a note card would be to just sweep through all the material, like a topics list like this, for example, and make note of what I might want to put on that note card. So for specific rules, for example. Anyway, and so then we have basic integration rules ranging from Riemann sums. Remember, that was like doing the rectangle thing under the curve, all the way to doing it exactly, finding the value of the plus c. So that's like saying, oh, when you integrate a function and you get the antiderivative plus c, how do we find the plus c? Remember that those are sometimes called initial value problems. And then the last topic is the substitution method, what I know is a particularly tricky method. And if you remember that homework, I tried to make a weekly schedule for this week, but I did make a weekly schedule and it's posted, but I'm having an issue opening it again. It's so weird. Whenever I try this, I try to open it up and it's the one from last week. It's so strange. I made a new one. If you look it up yourself, look, it says it's updated at 10:38, but it just opens up the old one. It's very strange. Anyway, the homework for substitution methods not due till next week. Keep that in mind. So, there's no homework due this week. This one's due next week, the homework, but it's on the test. And so the reason I did that is because I didn't want to force you to do it all and sort of overwhelm you in addition to studying, but being aware that it is on the test. And so you should do enough of them to feel confident doing a couple substitution problems. Okay. That's just sort of a quick run through of the topics, give you a chance to look at some of that review stuff if you hadn't already. General questions about anything in the review topics? I think someone was just about to say something. No? Okay. Let's pull up the quiz real quick. So I passed this one back. This is the one from last Friday. Generally speaking, most people did pretty well in this. Trying to remember a couple comments. One comment that came out of a lot of them, not a lot of them, like a handful, were remember to simplify compound fractions. So like on this problem, for example, right, you have the 3 halves in the bottom there, and we want to flip that upside down, multiply it, and end up with a non-compound fraction. So we end up with a 10 in simplified form. Or you could write it as 30 over 3 if you want, but just as long as it's not 15 divided by 3 halves. I'm not usually picky about things like that, but I mean, no one wants to look at a massive fraction. It just doesn't make sense when you write something like how do we know what this even means, right? We don't want to leave it like that. So anyway, I just want to sort of point that out. We want to simplify those things. Let's see. Other things that I saw. Nothing else is really jumping out to me at the moment. I think overall people did pretty well. Can I answer some specific questions about the quiz?
I didn't have any questions about the quiz, but could we possibly go over some of the Riemann sums things sometime later?
Sure. Yeah. Do you have some specific problems in mind, or you just want me to run through that topic in general?
Just run through an example. Like I usually have trouble starting them. Like I'm not sure where to begin with them.
Okay. Yep. Other questions about the quiz before we maybe shift over to that? Okay. Maybe I'll add a page to the test topics, actually. Maybe a good idea. I would encourage you to, if you're having trouble coming up with questions, or maybe there's actually one in here that we could look at.
Can we do a problem for each what's it called, topic from the test?
Probably not, because there's only so much time in this class period. So I would suggest picking out some specific ones. What I'm trying to point out right here is this test 3 review packet, I created. And so the problems on the test are going to look similar to this particular document. It looks like,
and of course it's on Blackboard.
Not the Newton methods one. Sorry, I forgot to remove these ones. We skipped over the Newton's method. Yep, it's on Blackboard. It's in Dropbox. It's pretty much everywhere you could possibly want to find this.
And where in Blackboard?
Test topics and practice problems and course documents. Anyway, I was just trying to point out, you might want to look at this one. Looks like I don't have a Riemann sum was in there though, so let me add one to here. And if you're not familiar with that word, because I didn't use it necessarily in the notes, but they use that word in homework for sure. When you see someone say, and I always have a hard time spelling this, are there 2 M's or 2 N's? I think it might be like that. When you see something that says Riemann sums, that just means using rectangles to add up area. I call it that in the topics. Let me see. Yeah, I did right here. I used the word AKA Riemann sums, but I said estimate the area under the curve using rectangles, right? So that's what that means. And just to do a quick example, I know, it's a little confusing maybe if you look back through the notes, but the idea is you want to break up the interval, write down the function values, and then apply the formula, right? And so there's 3 steps. The first thing you want to do is break up the interval into n pieces. So let me create the problem first, I guess. So let's estimate the area under the curve of f of x equals, how about 1 over x from 1 to 3. And let's use 4 rectangles. Right, so that's the key piece of information. This is like telling us the x values we're going to use, right? This is telling us how many rectangles there are. And so it's the number of steps we're going to take. And so we just do exactly what I just said. We break up the interval. We use the function values. I may not kind of fully go through this whole thing. And to be perfectly honest, on the test, I don't ask people to usually go through a full-on example like this. I oftentimes ask people to do parts of it, maybe set it up, maybe break up the interval, maybe write down the function value. Sometimes I'll present an entire completed solution and ask you to point out the mistakes. Sometimes it's a multiple choice question, but just to be clear, I'm not going to probably ask you to do a full, spend 10 minutes on one of these problems on a test. Just be aware of that. But if you understand this, it'll be good. So anyway, so we'll go from 1 to 3. So we're going to start with 1. Oh, let's figure out delta x. So we needed to figure out, this is like the step size, right? Delta x means the change in the x value. It's how we're stepping along. And so we want to start at 1, and we want to go all the way to 3, and we want to take delta x size steps. And so what is delta x? It's just the size of the interval divided by how many pieces you want. And so that ends up being 3 minus 1 over 4, right? You just kind of take these things, this thing, and that's how you figure out how many steps you're going to end up taking, right?
And that would be 1/2, of course.
Exactly, 2 over 4, 1/2. And so that means the distance down here is going to be 1/2, right? Every step we take down here is going to be 1/2, all the way to 3. Right, so it's just telling us, okay, start at 1, go to 3, step along by steps of 1/2. With me on that? So I'm just going to write. Yeah, go ahead.
I was just going to say, is n always given?
N is given. Yeah, it's usually you given some x values and n. Other things before we keep going? So you just, write down the values that you're stepping along from. You start at 1. The next one's going to be 1 plus 1/2. So that's 1.5. The next one's going to be 2. The next one's going to be 2.5. And the next one's going to be 3, right? So you just kind of step along by size delta x. And so the idea is those are the x values that you're using. And then you need to decide whether or not you're using left endpoints or right endpoints. Just as maybe I'll just do kind of a quick summary. If you use right endpoints, that means you start with the second one and go to the last one. So you would use x1 to x the last one, which is 4, to x4. And maybe I should say it's really the function values at those places. So f of x1, f of x4. If you're going to use left endpoints, you're going to start at the first one and go to the second to the last one, right? Because you're starting on the left-hand side of the rectangles. So you would use x0, and in this case, it's x3. I don't know if we want to keep going with this or you kind of sort of get the gist. I'm happy to keep going, but just in terms of how much time we have and using the most of our time or getting the best out of it. What do you think about that, Harris? Does that sort of clarify things a little bit?
Yeah, it's clarified some things up for me. I feel like if I practice a little more and just apply these concepts, I'd do better.
Yeah, I would just emphasize again too. Well, sometimes I give little hints like this, I guess. I'm going to ask you a question about this concept for sure. Is it the most important thing that we did? I don't personally think so. I think it was an introduction to integration and antiderivatives and sort of leading us into finding the exact area. And so, don't break your back like doing a whole bunch of these kind of problems. I would focus more on, Sebastian's asking about implicit differentiation or related rates. Like those are the kind of things that might be a little more relevant. Other people want to see more about this one or questions about it, or should we shift gears to something else?
Nah. What I really did want to see implicit rates, because you said that was about to be the bulk, or that was going to be a big chunk of what we about to do, right? On the test?
I don't know if it's a big chunk, but I'm going to ask you to do a full on one of those problems where I wouldn't, these ones that we're just looking at right here are more involved. So just in terms of the amount of time spent, I usually don't ask full questions like that. So, you're combining two different topics with what you're saying. You're saying implicit rate. So it's implicit differentiation, and we use that inside of related rates problems, right? So let me pull up the notes real quick just to clarify that. All right, so these two things are on the same page. You can see implicit differentiation and related rates. We talked about implicit first, and then we use it immediately inside related rates which are on the next page, right? So, as a quick reminder about how this worked, it was like instead of just having x's in a function and us taking derivatives with respect to x, all of a sudden we have hidden variables inside of functions that we don't really know about. So for example, let me kind of zoom in on this one problem. Instead of using this problem, see how it has t's and y's on the left-hand side. And what we're being told in part of the problem is that y actually has a t in it itself. And so if we're going to differentiate this thing with respect to t, let me switch colors here because red seems to be already used. So is blue, actually. Let me try green. All right, if we differentiate this with respect to t, what I've circled in green, 4t squared, is just a power rule, right? It says that right here, actually. Because we're differentiating with respect to t, and the t is just sitting right there. It's right multiplying the 4, and it's being squared, right? And so if I kind of zoom in just even on that, right, 4t squared, if I'm going to differentiate that with respect to t, it's just a power rule. But as soon as you differentiate the y one, right, this piece over here, that becomes a chain rule because we're differentiating with respect to t, and there's a t hidden inside the y function. It's kind of like maybe over here on the side, maybe we know that y equals 2t squared plus t or something like that, right? So we're like, we know it's a function of t, we just don't really know what it is. And so this is like a hypothetical thing, this thing I'm circling in green right now. It's kind of like y might have a t in it, but we don't really know what that function is. And so we know it's just, there's a t in there somewhere, and so it becomes a chain rule. So that's sort of I think if you can understand these what's going on in these two things, like how one of them's a power rule and one of them's a chain rule, that's an important first step to understanding this stuff. So let me just sort of pause there and see if there are questions about what I've just said.
And pretty much that would be like the 3y squared. That's pretty much 3x squared, but it's y. Y is pretty much representing x.
So it's kind of like this. Let's talk about the 3y squared part. So that problem had, what was it, 2t squared plus 3y. I'm forgetting what it was. 4t squared plus 3. That's okay. We can do it like this. But y itself is a function of t. Okay, so it's, and let's pretend that y is 2t squared, like I just said, 2t plus t squared or something like that. So we could rewrite this as this. Right, I just took this y out and it became y. Took the t out and it became y, I mean. Nope, that's not what I meant to do. I took the y out and I just replaced it with what it is. You see what I just did there? And I guess I'm asking specifically Jorge since he talked a second ago, but anyone else kind of see what I'm doing here?
I get it.
And so then if we differentiate this with respect to t, right, do you see now that this is a chain rule? Because we have 2t plus t squared inside of something being squared. And so hopefully you can understand at this point, this is a chain rule for sure. And so that's sort of the thing that we're thinking about here. And hopefully you can see the other one's a power rule, right? The 2t squared is a power rule. But let's focus in on the 3y squared. It's like, we know there's a t in here somewhere. We just don't know what the actual expression is, right? So the actual problem, we don't know this part of it. We don't know the expression for y. Like, this is just an unknown. But we know it's in there somewhere. And so that's what makes this one a chain rule. Thoughts about that? Right, because of this. So I'd love to answer a question, but let's just move forward and assume this looks okay. So if we're going to do this differentiation and there's a t in here, right? It's really important. The notation is important here. We're differentiating with respect to t, and there's a t inside of there somewhere. That's what makes it a chain rule. And so it would become this, right? You bring down the power, subtract 1 off the power, but then you need to multiply by the derivative of the inside piece. Right, do you remember the chain rule? The chain rule says f prime of g of x times g prime of x. Here's the f prime of g. Here's the g prime. Right, so when you differentiate this thing in shorthand, it becomes 6y prime. Let me just sort of pause there. That's an important first step there. I'm going to ask you to do a problem, like this for sure. And then these problems show up inside of related rates problems. So it's to Sebastian's point, the kind of thing I'm trying to say here is this is a double whammy compared to the Riemann sums. Like, you might see part of one Riemann sums question, but heck, you're going to be asked an implicit differentiation question alone, and then it's going to be inside of a related rates question. And so it's, in that sense, it's more important. Now, he said, he used the words, it's going to be a huge focus of the test. I wouldn't say that, and I wouldn't say like spend all your time doing that, but just trying to think about what's going to have more points associated with it, basically. Yeah. Stop there. Thoughts about what I'm saying here? Should we do an example? Have you looked at any of the, I put a bunch of example problems of this in the review section. Has anyone looked at any of that stuff? There's 3 individual documents and there's questions in the review packet I posted. Do we want to look at one? Do we feel okay about this and we want to go on to related rates?
Nah, can we look at one before we go to related rates? I can't say that I've looked at what you posted, like the material yet, because that'd just be a lie. But I do. I would like to look at one and then look at related rates, since this is gonna be inside the next thing.
So here's a couple right here. Let's look at these. And to your point, not to call you out or just in general, it's Wednesday. We've got our test on Friday. You don't have to look at all the documents, but you should be assessing what you know and what you need help with. And if related rates or implicit differentiation is one of those things, then you should be looking at those things. That's all. And at some point you need to do that, and it should happen before Friday. So anyway, that's all I'm saying. So here are 2 problems. We're going to look for an expression for y prime. And remember, y prime is dy dx. And in each case, we're assuming, or we're being told, that y is a function of x. Right? So if I rewrote this first problem, it would look like this. I'm just noting that y is a function of x. Okay, and what it's asking us to do is we want to do dy dx. I mean d over dx on both sides.
So of course get dx on both sides and then find out what's called y prime is.
Yeah, so when you do this, you're going to do some stuff. It's going to end up with, there's going to be a dy dx in there. Right? And then you solve for it. Remember these problems from the homework? We had a whole homework set that did this kind of stuff. And then, this particular question is trying to get you to plug a point in. But that's sort of the process. I would like to mostly focus on maybe we can do the whole thing, but maybe one step at a time. Like first differentiate it. Let's forget about the second problem for right now, and let's just do these steps one at a time. And I would ask you to try it, right? You need to be able to do this in a couple days. We just sort of reviewed it. Think about how that's going to work. Right? Someone tell me, what's the first rule going to be on that, the x cubed?
We're gonna do the power rule.
The power rule, great. What's the second one on the y cubed?
We're gonna chain.
That's a chain rule, nice. What about the right-hand side?
It seems like we are going to do the, what's it called? The multiplication, the product.
Product rule, excellent. All right, take 1 second and think about what that might look like. This is your chance to test yourself, right? See if this makes sense. If it does, wonderful. If it doesn't, you've got a couple days to figure it out. Now's your chance to, see if you get it. I'm going to kind of write the answer down over on the right-hand side.
Just like a quick question. What is f and what's g and yx cubed?
In yx cubed.
In the blue on the left. Like where you do the chain rule.
Oh. I see. Yeah, so this part is like, this is what you're talking about?
I'm just asking, like, looking at yx cubed, what is f of x? What's g of x?
So it's y of x. This is y is a function of x. We're not multiplying two things. Right? If you look at the original function here, it's just y cubed. And so I'm just noting, when I wrote this down, I'm just noting it's a function of x, which is what made me realize it's a chain rule. That's what I'm trying to note there. I'm not noting two things being multiplied.
Sure.
Can I just say something?
You can.
I think what he's asking is so f would be 3x squared and g would be 3x, sorry, would be x cubed, would be f. Then g would be I think it's yx cubed or yx.
I think you add it, but you just gotta flip it. F is gonna be y cubed, and then G is gonna be just x.
Okay. All right.
What's it called? I ain't had a problem with the chain one. I had a little bit of difficulty understanding realistically how you got the product rule. Would it just be because x, when you take the derivative of just x, it just became one? Is that really it?
Yes. Yep.
All right.
Yeah.
And then for
Were you gonna say something, Sebastian?
yeah, I'm trying to figure it out in my head so I don't just say it and then it's just like, damn, that's a
Yeah,
real
no, that's
stupid
fine.
question.
I don't know. I'm just making sure that you're thinking.
So then the y to the x again would just be another just like mini chain rule. You don't gotta do too much work. It's just kind of like follow the procedure.
Yeah, so when you do d over dx of y, and there's an x in there, it just becomes dy dx, which is just y prime.
Okay.
So it's kind of a chain rule. I mean, we were I was talking to Tommy about this.
So every time you do the derivative of y, it's going to become y prime.
Yes,
Yeah.
that's right.
I'm just trying to figure out how you got the x, honestly. The x in front of it. Because the y prime, it makes sense. That makes sense.
So if you write something like
The
this,
x, well,
y
remember,
equals 2x plus 1, right? This is saying y is a function of x, right? Y equals 2x plus 1.
Yeah.
Instead of writing y equals 2x plus 1, we're just saying, hey, y is a function of x. We don't know what this thing is. We just know there's an x in it. So we're just, when you write parentheses x, it's just saying this is a function of that variable. It's not multiplying it. It's notation. It's just saying there's an x inside of it somewhere.
Okay. And now we take the dy over dx. So now we're trying to isolate all the y's on one side, right?
Yeah, that's the next step, right?
All right.
Other questions about the derivative part? Right, so now we're trying to group, let me erase some of this stuff. Trying to group the y primes together. I like writing y prime just because it's easier. Hopefully that makes sense, right? The y prime equals dy dx, same thing. And so we want to group the y primes together and factor it out. I'll just make that note. Group y prime and factor. Right? This is a very common thing that we've seen in lots and lots of problems when you have things on both sides of the equation, you want to get just one of them. You get them on the same side, factor it out. Right, so it ends up looking like this. Let me know if you want to see the details here. Oops, I forgot the 4. Right, so I just moved like 2 things over to one side. Just trying to get the y primes together. so that you can factor it out, right? The whole point is so that I can do this. So let me just see if there's a question before I kind of finish it off here, but this is the whole point. We want to get that by itself, right? It's telling us to find an expression for y prime. So hey, now we only have one of them. It's multiplying, so we can just divide the rest of it over to the other side, and that'll be our expression.
Then we divide 3y squared minus 4x from 4y minus 3x squared. And then, yeah, we just have it on one side.
That's exactly right. Yep. Right? Is it kind of nasty and dirty, confusing? Yes, but we have this kind of nasty function to start with, where there were x's and y's on both sides of the equation, but we were still able to get an expression for the derivative. Like that's sort of the interesting point here. And then the last step, it says find the instantaneous rate of change at -1, 2. If we were going to finish this one off, we would plug in that point, and I'll let you do that if you wanted to try it, or you could look at the solutions. That would tell us the derivative. So that's the sort of thing, they have just tell you right now, I'm going to ask you to do sort of something like this. Some implicit differentiation thing where it's not an application, it's just some random function like these, just to see if you kind of get the idea. And then there'll also be, the one right after this, there's a related rates question, right? There'll be one like that as well, which uses this kind of idea inside of it. All right, let me see if there's some thoughts about this at all.
So we just found y prime, right? Like conceptually, like what is that? What does that give us? Like y prime equals the 4y over 3x.
Yeah, what does the derivative tell us? Anyone? There's lots of different words for it. I'll throw one out there. It's the instantaneous rate of change. That's another word for it.
I'm not sure, but now we plug in those numbers to see the instantaneous rate of change at that point.
Yeah, right. So another word for instantaneous rate of change is slope of the tangent line. The other descriptions are escaping right now. How the function's changing. The steepness of the graph. Right? I like to think about it just as the steepness of the graph.
It might be very basic, but would just the -1 be plugged into the x and the 2 be plugged into the y when we're plugging in these points?
Yes.
Oh, okay.
Yep.
So
And
we don't have to do it separately. We could just put it all into the equation, and that's what we get.
Right.
Perfect. We're good there.
These solutions are all up there too, so we don't have to do that kind of stuff. You can look at that later. I would love to just do a couple more things. Like it sounds like maybe a related rates question could be good, or substitution. I don't know. How do you guys feel about substitution?
No, we definitely gonna have to do a substitution problem
So
too.
the substitution already, I kind of
Definitely
did
got
go
to run that
over-
one for sure.
I did go over a few substitution problems on our homework, but I didn't understand some.
Okay. Can you pull those up, Jen? It'd be great if we could look at. I mean, I can do some on this practice sheet or whatever, and maybe there aren't any on here. I don't know, but it'd be better if we could do some and leave these for you to look at yourself.
Okay,
Yeah,
but
this
yeah,
is
can we
missing
go over
stuff.
this related rates first, I think?
Yeah, let's do related rates one. So let me kind of write a couple of the key things. And Janetta and I were talking about this yesterday. Maybe I just want to pull that up real quick. Is it this I was looking at with you? Yeah. So here are sort of the general steps. Let me just remind myself. Yeah. I won't go into that much detail. But no, this is in there from yesterday if you're interested. This is a conversation Janetta and I had. I'll just kind of make a quick note about the steps here. You want to draw a picture. That's why the circle's there. And the reason we draw a picture is because we want to note what's changing in it. Because 2, the things that are changing are functions of time. And so that means, you know, eventually we're going to do a d over dt of those things, and we're going to want to do f prime. Or if it's d over dt, just like we did a second ago of like f squared, it's a chain rule. So that's, you know, we draw the picture to kind of think about what's changing in this. Oh yeah, those things are functions of time. So that means when I do the derivative with respect to time, we're going to use implicit differentiation on that. And then what we always end up doing after that, can't really cram a step 3 in, I'll kind of do on the side, is we do d over dt. It's always going to be d over dt in these things because they're changing with respect to time. And plug in / solve for what you want. I know that's vague, but depends on the problem, right? But those are really the 3 steps. And if you want to see those kind of in more detail, look at this note. See my tab here? It's called Note April 20th, blah, 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 blah. There's some good information that kind of extends these ideas a little bit. Let me actually just run through that real quick because we did a quick example. So, you know, one of the problems we did had like a right triangle. I'm thinking about the one where the boat's being pulled towards the dock, right? And so we write the right triangle, and then we realize, oh, C and B are both changing. And so those are the functions of time, right? Those are the functions of time. And so then when we write down something that relates the variables, which I forgot to actually write down, step 2 is relate the variables in something. When you go ahead and you differentiate it with respect to t down here, you end up doing chain rules and implicit differentiation. And so we'll see that, you know, you can look back at the notes for a triangle example. Let's look at this one that's got this circle example. So it says, a circular shield of bronze is heated over fire and its radius increases at a rate of 1/5 centimeters per second. At what rate is the shield's area increasing when the radius is 50? Right, so we've got the circular shield. It has a radius. But the radius is changing because when you heat metal, it expands or contracts if it's not being heated, right? So R is a function of time, right? What are the information we're given? So we're given something about 1/5 centimeters per second. Someone tell me what that is. And then we're also being told the 50 part. And then what is it that we want? And what is it we're going to use? Who wants to provide any of that information here?
The radius increases at a rate of 1/5 centimeters per second.
Yep. So what is that? What is that in math terms? Or in calculus terms? It's the rate of change of the radius, right? How do we say that in calculus terms?
The rate of change of the radius.
Yeah. What we just said, what's rate of change? We just said that a second ago for something else.
So RT.
Derivative. Yeah.
Oh, derivative.
Right. Rate of change is a derivative. So this is R prime or dr dt, if you will. Right, so we're being told dr dt is 1/5. That's it's really important we see that, and you should realize it's a rate because it's centimeters per second. Right, that's a rate. That's telling you it's not just centimeters. It's not just seconds. It's something per something. That means it's a rate. What's the 50 thing?
50 is what the radius equals.
That's a radius value. Yep. What do we ask for? Right. It says at what rate is the shield? Well, it says at what rate is the shield's area increasing?
Oh.
Right, so the area is increasing. Thoughts about that?
So that means it's also changing?
It's also changing. Yep. So so area is changing. So how area is changing.
The
How do we say that in
derivative of
calculus
area.
terms? I'm sorry, say that again.
Derivative of area.
The derivative of area. So dA dt. That's how the area is changing. And what formula are we being told to use here?
A equals pi R2.
A equals pi r squared, right? The area of a circle. But I'm going to note here, A is a function of time and radius is a function of time. Because when the radius changes, the area changes. What do you think about the setup? Oops, sorry.
You have to find the derivative.
Yeah, so we want to start with A equals pi r squared, and we want to do d over dt of both sides. This is implicit differentiation, right? Hopefully we have an idea of what to do here. What do you think? What does anyone think? What is
R2, of course, is going to be chain.
Yes, this is going to be a chain rule. So what does this equation become? The whole thing. Does anyone want to read me what they think the entire? Yeah, go ahead.
Well, isn't pi gonna? Well, pi is it's a what's it called? A constant.
It's a constant.
So it's just gonna come out or something. Like you don't have to care about it.
Exactly. You just ignore that.
And yeah, we just find the chain of RT squared.
And what does that become?
I'm not really good at this, but 2R times R prime.
Excellent. I'm going to delete the r to the 1 just so you don't think they're both derivatives, but I'm just trying to indicate that we did the power rule there. Yep, 2r prime. And the left-hand side became dA dt, just to be clear. And that's the thing we want, right? We want that. That's what we're trying to solve for here. So that's good. And we have all the other information, right? We're being told the radius is 50, r prime is 1/5. And so we just plug the things in to get the answer, right? So this one becomes 50, like we said above. That's 1/5. And so dA dt equals 2 pi times 2 times 50 times 1/5, which is 20 pi.
Why is it pi times 2 instead of 2 pi?
Same thing. We pulled the pi out front when we did the derivative, and so I'm just kind of carrying forward with that.
Okay.
And is the 20 pi, is that centimeters per second, right?
It would be centimeters per second. No, it's area, so it would be centimeters squared per second.
Oh yeah, centimeters squared. Yeah, cool.
Cubed, actually. No, squared, because it's a two-dimensional thing. To think about those, it's good to think about the units, right? So R has, I'm going to write above the thing here, has units centimeters. And then R prime, we said, had units centimeters per second. And when you multiply those two things, you get centimeters squared per second. All right. What do you think?
That makes sense.
That's what I like to hear. Anything else about this? Should we jump over to substitution? Let's sub. I'm going to jump back over to these notes again because I think there's good stuff in here from this. Nope, just kidding. I didn't put anything in there about that. So let me go back to that thing I just had open. And I will add another page. That's not what I had. This is great. Nope. There we go. So let me just do a quick rundown of substitution in case this is still really confusing. Substitution. Remember, we want to undo the chain rule. Going chain rule crazy, I feel like, in this section. And as a quick reminder, this is what the chain rule is. If we differentiate something that's a composition, we get f prime of g of x times g prime of x, right? We just looked at that a little bit today in a couple contexts. And so what we're doing in the substitution method is we're integrating the right-hand side of that, right? So when the substitution method gets used, it's when we want to integrate, i.e. undo the chain rule. Right, so this is sort of what we're trying to do here. We had learned previously the chain rule, and remember, integration you can think about as undoing derivatives. And so we're trying to undo the chain rule. And so that means, you know, when you're looking, you're given something that looks like the integral of a chain rule. Notice the key things about it. There's a g in there and a g prime. And so that's going to be the u, right? You let u be g, and then g prime is going to be u prime, right? And so the thing that I'm trying to kind of point out here in thinking about the chain rule is to choose u, you want it to be the g, whatever g is in the problem. Okay, so what is g? And so you choose it such that, so choose u equals g as x such that u prime, which is g prime, is also in the problem. So I'm trying to make a big deal about how to pick u, obviously because it's the first step to getting the question right. But in terms of just getting points on a test, like if it's a 5-point question, just writing u down is going to get you 2 or 3 of the points. Right, so the thing that you're looking for in a problem is something in there that when you take the derivative is also in there, right? If I kind of look at u, it's like, oh, well, look, let me do another color. Oh, well, look, u is g, g is in the problem. And when I take the derivative, g prime is also in there. That makes me feel good that that should be u. So as an example, it'd be like, or the first example we looked at was something like this. And I would expect this sort of kind of level of difficulty. We looked at some harder ones, but I'm just going for something a little more straightforward on this test. Maybe it's more complicated on the final. On this test, this is what we're looking for, right? So when we're thinking about u, and everyone should be thinking about what is u, it should be something that u prime also in there. And oftentimes it's inside something else, but it doesn't have to be. Sorry, someone was about to speak. Go ahead.
X squared plus 1.
Yeah, x squared plus 1. Because when I do u prime, and the better way to write u prime in this case would be du dx. Because that helps with the substitution part, right? When we do du dx, we get 2x. And hey, they're both in there. U is in there, and u prime is in there. So that makes me feel great. That's how we move forward in this problem. I'll just pause there and see if that looks okay.
this is the overview, or this is the problem that we're about to go over?
We can finish this problem. I'm just trying to see if there's thoughts about what I said so far. You get how to choose you?
Yeah,
Special.
it has to be something else that's in the problem. So make sure you pick a good one. Make sure when you get the derivative of what you picked, it's still in the problem to
There we
the
go. Yeah,
to
I
the
like that
majority extent.
explanation better. But yeah,
It's
definitely make
facts,
sure it's a
though.
good one too. But yeah, to explain further, like you said, a good one means the derivative's also in there. So yeah, let's keep going with it. So you don't have to do this on the test, but I'm going to rewrite this in a way, hopefully that sees how the substitution works. Right, so I'm just rewriting it below, because what we just did is we said, hey, this is going to become u. And this part right here is going to be, and I didn't actually do this. Let me finish that part up here. So this says du equals 2x dx. Right, sorry, I forgot to move the dx over. That's important because that means, that's right here, right? And so 2x dx just becomes du. And so it lets us transform this problem that was really nasty at first, right? Something being cubed, a polynomial being cubed, and its derivative next to us, i.e. a chain rule. And it lets us transform it right into just u cubed du. Super easy.
Now we just find the antiderivative.
Now we just do the antiderivative. What is that, Janetta?
It's going to be 4 u fourth divided by 4.
Yep. Anything else that we should throw down there?
Times 2x times du.
Nope, that's not what I'm getting at. So after we do the antiderivative, you don't write the integral sign or the du. I'm getting at something else that we always write down in these.
Oh, plus c, my fault.
Plus c. Good. The family of antiderivatives. And then you plug u back in.
So right after that, you don't ever put dx back in, like dx doesn't.
Correct.
Okay.
So from here to here, you just plug u back in. Right, those are instructions. These things right here, the integral sign and the du, mean we're going to integrate, like the s thing literally means integrate u cubed with respect to u, the du part. And so when you do that, you don't write it anymore. Just like it's a notation thing. It's like when you write limit down, you write limit every single time until you actually plug the number in. It's like, it's instructions. It's same thing with the d over dx, right? It's like when you write d over dx of x squared, that's instructions that say differentiate this thing with respect to x. And then when you do it, you don't write it down anymore. Alrighty. What do you think?
Well, I had some problems on the one on WebWork though.
All right, let's look at that one. Any questions about this one?
This one was smooth.
Yeah, so the answer is x squared plus 1 to the 4th over 4 plus c, right?
Yep, that's it. Can you read me the one you're looking at, Janetta?
Actually, no, I don't have, I can't get to it right now, but it was the first one. Like, it's usually the ones that have fractions.
Yeah, so there's a number in there or something. Let me pull that one up.
Yeah.
Okay. Yeah, this one's a little tricky to start out with, I would say.
Because for you, I did start off with, I'm pretty sure I thought that it was x squared plus 8x.
Mm-hmm. Well,
And
give me 1 second. Let me pull it up here. Okay. All right, so yeah, so what is u? Right, we want it to be something that when you take the derivative, it's also in there. So what are you thinking?
Yeah, I thought that u was x squared plus 8x.
I like that. Because when you do du
And then
dx, you get 2x plus 8. How are we going to make that look like something that's in there?
then you'd have to divide that by 2.
Yeah, or factor 2 out, if you will. Right, so you could do
Yeah.
like, how's that look? Right, and that's nice because x plus 4 is in there. And moreover than that, not just the x plus 4, the x plus 4 dx. I should have circled that whole thing, and we're going to be able to replace that whole thing there, right? But notice how, maybe this is your problem, the 2 is not in there.
But I thought that we were able to like put it on the other side, like 1/2 du or something like that.
Absolutely, yeah, so that's exactly right. So then, since we're seeing that the 2 is not there, you move it over to the other side, and now we can make the substitution because this is the entire right-hand side is now part of the graph, right? Great.
So what happened with the 2 there? Like,
Right, do you see how the x plus 4 dx is in the problem?
yep.
2 is not. And so we can't leave it on the right-hand side and make a substitution with du because there's nothing to replace the 2 is not being replaced. And so instead, we're going to take the constant and we're going to bring it with us when we make the substitution.
Okay.
In this kind of way. So let me rewrite the problem again. The problem is, and I'm going to write it like this. Hopefully this makes sense. I'm just going to separate the two things. Same exact problem. I didn't change anything. I just brought the x plus 4 over and multiplied it, right? And I just wanted to do that because we're going to make this substitution. This becomes 1/2 du. And the other part, 1 over x squared 8x, is 1 over u.
So wouldn't it be u to the -1?
Yes, but we have a specific rule for 1 over u.
So wouldn't it become like ln or something like that?
It becomes ln, right? How's the substitution look, right? Because then we ignore the 1/2 and we just do 1 over u du. Thoughts about it?
Because
You see
I
what happened there
swear I
with-
tried that.
Okay, we can keep going. Did you see what happened there with the 2 though, John?
Oh, yes. Yeah. Well said.
Okay. I'm just looking at the answer real quick here to make sure there's nothing funky about it. Yeah, it seems fine. Okay. So natural log. And then we plug the u back in. What was u? 8x squared, x squared plus 8x. And that's the answer. But I'm noticing that the plus c is part of the answer, right? You don't actually have to type the plus c in because it's part of the answer. That's, see how it has a plus c after it?
Okay. Other ones were hard for me to understand, but I don't think you're going to put it inside of the test. So I guess I'll try to get onto them. I guess I'll try to understand it.
I'm just looking at yours. You're talking about number 3, maybe?
I actually had some trouble solving that one. Can you
Which one?
number 3?
How'd you get the 1/4 before you leave to number 3?
It's 1 over u.
Oh, tragic. All right.
Other thoughts? Yeah, so number 3 is actually kind of similar to this one in the way that you choose u. We only have a few minutes left. I have a meeting at 12:15, so I can't stick around after that. But let's look at 3. So everyone's looks a little different, but it's just different numbers. It's the same kind of setup. Just gonna kind of go right in on this one. What were you thinking about u should be, Jorge?
2 plus e 3x.
Yeah, that sounds good.
Oh, well, 2x.
Same.
Yep, that looks good. So what happens when you take the derivative?
Becomes 3 times e 2x. 2x.
So it becomes 2e to the 2x.
Oh, sorry. Yeah, I'm looking at mine and I have
Oh,
a
okay.
3.
Okay.
I have a 3 on top, so that's fine. Sorry.
No problem. Good. So then,
Wait, when we do the derivative of it, doesn't it become just ex squared? Ex 2x?
so it's a chain rule. So you keep the e to the 2x, but then you multiply by the derivative of the inside,
Oh yeah, my
right? And
fault.
so the derivative of 2x is 2. That's where the 2 out front comes from.
And then you divide 2, of course.
Yes. So then you have du equals e to the 2x, and you move the 2 over to the other side, right? Because when I'm looking over at the original, there's no 2 here in front. And so that's what made me do that. Is that okay? You move the 2 over, kind of skipped a couple steps there, but not skipped, but is that right?
Yeah.
So then when I make the substitution, this becomes, again, integral of 1 over u times 1/2 du. So it's a similar kind of thing where you have 1 over u again, and you're going to do ln. Let me just pause there and see if that looks okay. I forgot to write dx in the last thing. Sorry about that.
Why did you circle e raised to the 2x in the very top where u equals?
Janetta had asked where the 2 came from, and so I originally started talking about how this is a chain rule, but I didn't write it down.
Yeah. All right. No, sounds good.
How's that look, Jorge?
Good.
So what's the next step?
You would just get the antiderivative.
Which is?
It's going to be ln, well, 1/2 times ln u, yeah,
Let's
plus
see.
c.
And then we just put the u back in.
What happened to the s? Or the integral sign?
We did the integral, right? When you integrate 1 over u, it becomes natural log.
Oh, so once you take the antiderivative, you don't have to put the s no more?
So the s and the du is their instructions. That's what I was talking about a few minutes ago. It's telling you to take the antiderivative. So after you do that, you don't write it down anymore.
Okay.
And for the ones that have, like, they're asking you for the definite ones, we're supposed to find it first and then, like, put the numbers in.
Yeah, so if there were numbers on this particular problem, I'm going to write them in red. Like if it was 0 to 4 over on the bounds, the next step in this problem would be to plug the numbers in. First plug the 4 in, then subtract, plug the 0 in. Right.
Okay.
Professor, what are you giving us on the test?
My best wishes.
Oh yeah.
I'm gonna put a unit circle on there. But I would say if you want specific stuff on there, then you should write it on your note card.
All right, cool.
Would you want some? I guess when I was thinking about that, I didn't really know what to put on there other than like everything. So that's usually when I just defer to your note cards.
Okay, that's fine.
All right, I do have to run to a meeting, but the other sort of quick questions, other things like that that you're thinking about?
Can I have a meeting with you tomorrow?
Let's see my schedule here tomorrow.
Can I join that?
Yeah,
I
I'm okay
just-
with the 2 people meeting.
I could
Yes,
do
sir.
something in the morning if anyone's available.
Yeah, I'm okay with that.
What time in the morning?
You tell me.
What's tomorrow? Tomorrow's
Could we
Thursday?
do? Could I ask you to do? Could we do noon? Is that possible?
Noon?
Or like 11:30, 11:30 noon, something like that.
I'm okay with that.
All right, 11. Let's do 11:30.
Okay.
I don't think I'm gonna be able to make that
When are you around?
because I got a lab at 12:30, and that go until like 3:15.
We're gonna start at 11:30.
All right, that's fine. Then.
All right.
How,
We'll
how
use
should
this
we get into this meeting? Just join this thing again?
same link. Yep. Let's use the same link.
Okay. Then
All right,
yeah.
thank you.
All
Thanks.
right. I got to run to this meeting, guys. Send me messages, emails if you want to chat.
Okay. Well, thank you.
Bye.
Bye.
Thank you.